Good morning, good afternoon, and good evening. I'm your host, Aya Takasen, and I am here with our presenters, Amber Koibi and Tim Brado.
Hello.
Hi, everyone.
Thank you for joining our webinar series, Beneath the Surface, Non-Destructive Elemental Analysis of Batteries Using XRF. In this webinar series, we will discuss how to leverage X-ray analysis techniques to gain insights into battery performance. Our expert speakers will share the best practices in real-world applications. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window. And we'll be taking your questions live during the webcast and answering them during the session, so please do not wait until the end to ask your questions. Please submit those questions via the Q&A button at the bottom of your screen. We will not be monitoring the raise the hand function. We will try to answer as many questions as we can during the webinar, and we will respond to any unanswered questions directly after the session is complete. If for whatever reason you have a difficulty viewing the webinar live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. Okay, with that said, I will turn it over to Amber.
Thank you, everyone, for taking the time to attend. Like Aya said, we're talking about non-destructive elemental analysis of batteries using XRF. So through this presentation, we'll hope you'll learn what is XRF. XRF analysis may not be widely used in the battery space for some, but this technique can be used in a wide variety of ways. Why use XRF? Like the technique suggests, this is a non-destructive technique, but there are some other reasons that XRF may be a good fit for your materials or lab. We'll also cover where in the battery process XRF can be used. And we'll wrap up with some examples of materials we've worked with. But before we get started, we'd like to get a feel for what techniques those in the audience use.
Okay, so let me start the first polling question. Which elemental analysis technique do you use if you use one? And the choices are ICP, XRF, XPS. You might use something else, and you can choose other, or you might not analyze any elements. The answers are coming in fast. I think most of you answered it. I'm gonna wait a couple more seconds, and I'm gonna close it in 3, 2, 1. Okay, let me share the results. So 78% of you in the audience said XRF. That's what you use. And next to it, both 33% ICP and XPS, and 11% other, and 22% I don't analyze elements.
Interesting. Well, we'd like to hear what those other techniques are. We'll definitely be talking about XRF and some ICP today. And if
Okay,
you don't
here's,
analyze,
I'm
go
sorry.
ahead.
I
No,
was
you're
gonna say,
good.
if you chose other, maybe you can share what you use in the chat.
For sure. All right.
Okay.
For those that aren't as familiar with XRF, though it looks like a majority of the audience is, we'll spend a little time reviewing the techniques so you have a general understanding of what the technique is and how the instruments work. So to begin this discussion, we're going to look at an everyday object. This object hopefully looks familiar to everyone in attendance. We'll imagine this is a lithium-ion battery for the sake of this discussion, and we'll call him Bob. So while we understand that Bob is a battery, if we take a closer look past the components and down at the atomic level, the object Bob, the battery, may look just a little different. So many of you are likely used to working with the periodic table as you're doing a lot of elemental analysis. And this is what makes up Bob and all of other matter, of course. This table is going to be another of our friends throughout the presentation, so we're just going to get familiar with it. But for Bob's close-up, if we take a closer look again down at the atomic level, we can see that Bob is comprised of a variety of elements. For this, we're going to simplify it down to nickel, manganese, cobalt, and iron. If you've been attending the various episodes of this series, in XRD, sometimes the structure and organization of elements is important to know. For XRF, however, we're just looking at those basic building blocks and answering the question, what elements make up this material? Or in this case, what makes up Bob? So we'll begin this by discussing the theory of X-ray fluorescence. To understand XRF theory, we'll take an atom of nickel and we'll look at its atomic structure. We all remember learning that atoms in school. Here's the center of the atom, the nucleus here, surrounded by electrons in their respective shells here. So in X-ray fluorescence, we use an X-ray tube and irradiate the sample with primary X-rays, shown in red. Those X-rays kick electrons out of their shells, as shown here. And electrons from the nearby shells will jump to fill those valence states. So as those higher order shells fill the void, it releases an energy in the form of fluorescence, as shown here by this K-alpha emission line. And depending on which cell the electron is jumping from determines the line that is emitted. So as we can see here, we're jumping from the M shell to the L shell, releasing an L alpha emission line, from the M shell to the K shell to release K beta. And these are each seen as a peak by the spectrometer. So when we talk about spectra, these are the peaks that we're talking about. While the theory remains the same, there are a few different types of XRF techniques. The primary two that we're going to discuss in this presentation is energy dispersive X-ray fluorescence, or EDXRF, and wavelength dispersive X-ray fluorescence, or WDXRF. While there's a lot of details out there, you can compare a lot of different manufacturers. Here's kind of just a simplified, more generalized list that covers a lot of the products on the market. So the first we'll talk about is format. So energy dispersive are typically going to be smaller units. These are going to be in the handheld or benchtop state. Whereas for wavelength dispersive spectrometers, we're typically going to be in a benchtop, or obviously what you're probably more familiar with is a floor model unit. The tube types are generally going to be something roughly in the middle of the periodic table. So for energy dispersive, it could be silver, palladium, rhodium. There's a few others. For wavelength dispersive, it's typically palladium or rhodium source. For wattage, the main difference between energy dispersive and wavelength dispersive is going to be the power. So those benchtop and handheld units are going to be at much lower power than our wavelength dispersive units. For analysis range, energy dispersive can cover as high on the periodic table as sodium down to uranium, whereas wavelength dispersive are going to be have the ability to cover beryllium through curium. So we have a little bit wider analysis range with a wavelength dispersive unit. For your atmosphere options, we'll talk about this a little bit as we talk in the sample prep, but you can analyze in air, helium, or vacuum depending on the energy dispersive spectrometer. In wavelength dispersive, we're typically talking in helium or vacuum. And at the end of the day, cost is always a main factor. So typically your energy dispersive spectrometer is going to be a lot cheaper than your wavelength dispersive spectrometers. So it just depends on what you need to get the job done. So of those two techniques, the first we're going to look at is energy dispersive X-ray fluorescence. For this technique, we'll start with the source for our example. So the X-ray tube is going to emit primary X-rays that are going to interact with the sample. Fluorescence from the spectrometer is going to be collected then by the detector. And this is what produces that typical spectra those of you that may be using energy dispersive X-ray fluorescence are used to seeing. So we'll see that there's a little bit of difference between energy dispersive and wavelength dispersive here. Due to the more simplified mechanics, like I said, these instruments are typically smaller and more mobile. So here's a few examples of benchtop EDXRF instruments. The next QC series and the next CE series are examples of instruments that are fairly portable. And many people will move these around their lab or maybe different testing facilities. I like to say you can take these home in your backpack. Sometimes we'll take these on the go, pick them up, carry them around the lab. If they're only 20, 30 pounds, they're pretty portable. We typically refer to these instruments as plug and play, as they don't require a lot of space for setup and they don't require a lot to get them up quickly. So these can typically be set up by the operator and no need for additional service or support. So now that we've talked about the energy dispersive units a little bit, let's move on to WDXRF instruments. For our wavelength dispersive X-ray fluorescent units, it's just a little bit different. While wavelength dispersive spectrometers come in different flavors, we're going to talk about a sequential WDXRF. So this graphic is going to be set up in a tube above configuration, excuse me. Depending on what you're used to working with, it could be tube above or tube below. I personally am a fan of tube above just for sample prep purposes. So we'll begin with the X-ray tube. That's going to emit primary X-rays, typically a rhodium or palladium source. That's going to hit the sample. From the sample, we're going to emit our fluorescent X-rays. Those are going to be collimated. This is where we get a little bit different. We're going to strike an analyzing crystal and cause diffraction. So we're going to target a specific wavelength and move that detector into the location of where we anticipate to collect that spectra. So in this case, we're talking about manganese. Again, we would move the crystal in the detector to collect a different wavelength, in this case, iron, and thirdly being nickel. So this is a little bit different from energy dispersive X-ray fluorescence in that crystals and multiple detectors are used and there's more moving parts. But this helps explain that sequential nature and why it's called wavelength dispersive. Here are a few examples of WDXRF units. So while these can vary in size and power, the Super Mini 200 on the left is a 200-watt system in comparison to the Primus series, which are 4 kilowatts on the right. These typically aren't considered mobile like the energy dispersive units are, but the wavelength dispersive units are going to have a much higher power and allow you to analyze a much wider range of elements. So now that we've had a chance to review the two instruments, we'd like to ask another question.
Okay, let me start the next polling question. Okay, so the second question we wanted to ask the audience is, do you have an XRF spectrometer? We remember that some of you said that you do use XRF. And you might say, yes, I have WD XRF, or you might have an ED XRF, or you might have both WD and ED XRF, or you might not have one. C. So about 2/3 of you answered the question. I'm going to wait for a few more seconds. It's kind of fun to watch all the answers coming in. Okay, so I'm going to close this in 3, 2, 1, and share the results. Okay. So about a half of you said that you don't have an XRF, and about a third of you said you have both WD and ED. Then the rest of you said that you have either just WD or ED XRF.
Interesting. So if you
And
don't
Amber,
have XRF, go ahead.
Well, I was going to say, Amber, we have also a question from the audience when you're ready.
Oh, perfect. Yeah, we could take questions now.
So we have a question. Which XRF should I use for battery analysis?
So that's going to depend on what the need is. So again, we've talked energy dispersive versus wavelength dispersive. In the case that you're not needing light elements, you may be fine on an energy dispersive unit. Detection limits are going to vary. So again, if you're looking at trace level elements, you're probably going to be wanting to work on something a little bit bigger with a little bit more power. But if there's something specific you're interested in, let's talk after this presentation.
Great. Thank you.
Sorry, my screen was delaying there. All right. So if you didn't know much about XRF prior to this, hopefully you have a general idea of how XRF works and how the instruments work. Though it seems like there's a good amount of us that are familiar with XRF, which is good to hear. So let's talk about now why you'd use XRF and what the benefits of the technique has over other techniques out there. So for traditional analysis techniques, we did poll earlier to see what you're actively using. So there are 3 common techniques that we've generally associate with the battery market. Again, if you're using something different, please put in the chat what you're using. We're interested to see what other elemental analysis techniques are widely being used. But the first that we think of, or at least I think of when I'm talking to customers that are interested in elemental analysis with battery, is inductively coupled plasma mass spectrometry, or ICP-MS. So hopefully everyone's familiar with that. It seems like there's a lot of people that are using it, which is to be expected. The other being XPS, or X-ray photoelectron spectroscopy. So this is kind of our cousin technique, if you will. X-ray fluorescence, which is why we're all here. But again, there's many others out there and we're interested to hear what you're using if you're not using one of these techniques. So one of the biggest reasons that customers will discuss in terms of why using one technique over the other would be sample preparation. In the case of traditional ICP-MS, you typically need to get the sample into solution, which requires acids, heating, and a lot of potentially dangerous prep work. The beauty of XRF is that we don't have to get the sample in the form to calibrate the instrument. We just calibrate the instrument in the form of which the sample already is. So if you're sweating it like Bob was, please don't. XRF sample prep can take on many forms. So where there's a will, there's a way. We can work with solids, which could be good for your components or flat parts that are already pre-existing. We can work with powders, which is, I would guess, is what a lot of the audience is probably working with. You'll see some prep examples later in this presentation for these powder samples. And we can even work with liquids. So in the case that maybe you're analyzing your bath material or related, we can analyze liquids as well. For sample prep, there's a lot of options for XRF, and I don't want this diagram to be overwhelming. I just want to emphasize that we deal with many types of materials, but they typically can be boiled down to following 3 general preps. The first being metals, or what I previously called solids. The second being powder. And in this case, you're probably working with a material that then needs ground or is already ground. We can then pelletize and produce a brick of some kind and measure. Or if you've got it, it's already in powder form, we're just going to dump into a sample cell and then measure as is. Again, these can be modified to meet your needs. So if I'm going to say that where there's a will, there's a way. I say that a lot when we talk about samples in the lab. And that's pretty true for XRF prep. There's always usually a way to get reliable data. It just depends on how much time do you want to spend and what prep materials do you have on hand. So we can usually find a way to prepare a material to meet a lab's needs. And then, like I said, again, we also have liquid analysis. So an example of a common prep, just to give you an indication of what this would look like, would be a form of a pressed pellet. In this example, all you're really going to need is your sample, your press, and your die assembly. So in the case of this, you'll just take your sample, you're going to pre-weigh it, and then load it into a ring and press the die on top. Load it into an automatic press, hopefully automatic. I'm lazy. I like automatic. If not, you could do it manually. I'm here for it. So we're typically going to press these up for 12 tons. And then we're going to be given a sample like above here. So we'll see this guy again later. But this is a really good way to give really repeatable, reproducible data. And again, we can run this multiple times. It's going to be very stable. It's not something that you're a one and done like you would on some other techniques. So if you decide you want to go look at something else in the material, you can reanalyze it or use it for another technique. Another common reason that we see people looking at XRF analysis over some other techniques is the wide range of the analytes. So here's a periodic table again. And when we talk about XRF analysis capabilities, it's honestly easier just to cross out the elements we can't measure than circle the ones that we can. So while we can't analyze a few materials, we can cover most needs. In the case of lithium, in the case that you are needing to quantify lithium in this case, I would definitely tell you ICP is still your way to go. And these techniques can work hand in hand. I don't want it to be an all or nothing. Hopefully you've got multiple techniques in your lab, but this is would be a good application that ICP and XRF can go hand in hand in the case of lithium. And while we can analyze most of the periodic table, ease of use is a huge contributing factor for why I see a lot of individuals moving to XRF over things like ICP. So one of this is going to be prep time. So typically sample prep is going to take minutes. I'll say 5 to 15 minutes. If you're just dumping some powder in a cup, it's going to take a lot less than 5 minutes, I promise. Whereas typically it's going to be hours on ICP. In the case that you're calibrating for a wide range of elements. Another reason is the prep materials that are needed. In the case of ICP, you commonly are going to need acids, glassware, your centrifuge, anything to digest, your hot plate. For XRF, we're not having to worry about anything hazardous in this case. It's just going to be a press and a die assembly in the case of pressed pellets. For analysis time, quick turnaround time is another key reason that XRF is starting to become widely looked at. Analysis time is going to take less than a minute to 30 minutes, I'll say. Again, it depends on what you're looking for. I'd say we can get you out in under 30 minutes easily for most materials. ICP-MS can take minutes as well. Sample recovery. So in the case that you are needing that material for another testing technique, ICP-MS typically not going to recover that sample once it's digested. Whereas for XRF, if we choose a prep, such as dumping into a sample cell, or if it's pressable on its own, the sample can then be reused for whatever else you need to do. Or if it's a valuable material, again, you've got 100% recovery then. Calibration setup, and I'm going to say calibration time are kind of going to go hand in hand. Setup, in this case, ICP-MS, you're doing individual elements, whereas XRF, we're typically going to calibrate for all elements at once. We call it one calibration. It's all going to be done at the same time. And that amount of time it takes is going to depend on the amount of analytes present or what you're looking for. So calibration time, again, can take a long time on ICP-MS. XRF is typically going to be about an hour. Calibration upkeep. This is a common complaint that I hear when talking with individuals that are working between the two techniques is calibrating that instrument. It's going to take daily plus, I say, if you're having any humidity temperature changes in the lab that you're having to accommodate any changes to the instrument. Calibration is very touchy in some cases. In terms of XRF, that's something that is really nice about these instruments because they're self-contained. Everything stays stable. There's not a need to recalibrate often. We recommend recalibration every 6 months. But I'll be honest and say that I probably don't recalibrate my instrument every 6 months. I don't see a lot of drift or a lot of need to. And then the other part where ease of use comes into play is who can operate the system and who can calibrate. So for ICP-MS, you're typically going to need somebody that is comfortable with what chemistry and can do dilutions and digestions. XRF is commonly just set up with the calibration, and it's an open access instrument. As long as somebody can come in and tell the instrument where the sample is, what position, and what method it needs to run, anyone can walk up and use the system. So it's nice that you've got more than one department, hopefully at that point, that can come in and operate the instrument, and you don't have to have a dedicated operator or calibrator. Another reason people like XRF and why we're seeing it more commonly investigated is the types of analyses we can provide. So the first is going to be qualitative analysis or scanning. So in this case, we're able to scan for a wide range of elements and still provide data without any calibration. In the case of semi-quantitative analysis, that's where we're able to then use maybe a factory calibration. Again, nothing needed on your side, already installed on the instrument, to then provide some sort of quantitation behind that spectra. So now we can find out what's in there and roughly how much of those analytes are present in that material. And then the last being quantitative, and this is what we typically think about for XRF, is that we calibrated the instrument and we have a very good idea of how much of these analytes are present in this material. So I characterize these in 3 different ways, and we'll talk about them a little bit more. So the first type of analysis being qualitative analysis. So most XRF spectrometers can provide qualitative data. And this helps answer that question of what is in the sample. And we can know nothing about the sample, analyze it without a calibration, and determine what analytes are present. So here's an example of spectra produced from a qualitative analysis. And you can see there's a variety of elements present along with an intensity or signal. And this could very well tell us what's in Bob or his components, just from a scan. So if we combine that qualitative for that scanning function with a factory calibration, so these are typically factory installed, there's nothing that is need done on the operator's part. We can now get a reasonable qualification for elements present, not only answering, hey, what's in here, but also roughly how much of those analytes are in here. So we now have spectral data for verification purposes and reasonable results without the need for a large calibration process. And then for a quantitative method, so that third type of analysis, if you will, you'll ideally use a standard material that has a certificate with values. Another option in this case would be if you have another trusted technique like ICP, where you have in-house materials that you can then do either do ICP analysis or have outsourced to another lab to produce those standard values. Those can be used in place of like a certified material. So you'd prepare your standards, and the goal is that the standards are going to be in the same matrix as your unknown materials. So these are all going to be prepared the same way. These are all going to be made of the same material. So once you've got your standards and you've got your values, we're then going to collect intensity on the spectrometer. So earlier we saw that spectra. We're not going to see spectra in the case of a quantitative analysis. But the instrument is going to then associate an intensity. Here on the left, we're going to collect an intensity with those samples, and then you have your standard values from your certificate to produce your calibration. So we'll collect the intensity of the elements for Bob's building blocks, and then we're going to tell the system what those certified values are. And now we have the intensity and what to expect for concentrations of various elements. So then we're able to run all of your unknowns back against that. And I think that's going to bring us to our next section. Do we have any questions, Tim?
Yes, we have another question. Do I need to worry about adjusting the pass-fail threshold after switching from ICP to XRF?
So in the case of going from ICP to XRF, the pass-fail threshold is going to depend on what elements you're looking at and what concentration range. So in the case of, if you're talking ppb, parts per billion detection range, something like that, that's not for XRF. That's going to be ICP. I wouldn't switch to XRF for that. But in the case that you're looking at ppm or mass percent, we can calibrate the instrument with very good precision. I don't think that you would have to worry about adjusting any thresholds in that case.
Right. Thank you.
I think we got another question in the chat.
Oh, okay.
Can you say that, Tim?
Yes, I do. We have a question. How do we determine the detection limit of the spectrometer?
So detection limit for the spectrometer is going to be like 3 times the standard deviation of background. So basically you would run a blank material and then we can do a calculation off of that to determine what the detection limit would be. And that detection limit is going to change for each material. So if you were to run, let's say, a powder cathode material versus a liquid bath material, the detection limit for nickel, say, in both of those materials is going to be different because the X-rays are going to escape very differently between those two materials. But if there's something specific that we can follow up with after, I'm happy to help with calculations.
All right. Thanks, Amber.
All right. So we've talked about what is XRF and why we would want to use XRF. Let's talk about where in the battery space XRF is being used. And if you've got any feedback on this, obviously we're open to hear it as well. So we're calling it the process. So here's our cartoon of the battery process. And we'll briefly walk through this process, just kind of indicate where we currently see XRF being used. So the first step is mining. So go all the way back to the beginning, we're working with the rock material. This is near and dear to my geologic heart. In the mining process, it's common to see XRF used for ore materials and checking grades of mine materials. So you might see handhelds that are going to be doing rough screening on materials, or even benchtop or floor model energy dispersive or wavelength dispersive units commonly being used for screening where higher precision over the handheld is required. So we're definitely in the mining part of the process. In the refining process, XRF is used for elemental analysis just to ensure quality control of incoming product to be received by a company. It could also be used for looking at contaminants along with process killers that could be induced as part of that refining process. And we'll see some examples of that later. XRF could be used in the mixing process. So if you're ensuring ratios for NCM powders, for example, we'll see an example of that in a minute. It's very good application. For coding, drying, and calendaring, we're not going to talk as much about this today, but there are inline XRF systems that can be used and are used in monitoring quality control for the coding process. And finally, those batteries are assembled and packaged. and they're finally going to be used. So if you attended Angela's talk on the X-ray imaging, you saw how our imaging instruments can play a role in looking at battery defects. And then back to XRF again is finally part of that recycling process. We come full circle. XRD and XRF will come back in to assist by looking at the elements present and help determine next steps for that material or how that material could maybe be reused. So we've covered the what, the why, and the where. So now let's see how is XRF used in the battery space with a few examples of materials we've worked with. So the first example I'd like to look at today is an NCM cathode example. And to begin the whole process, we'll start with sample prep. So this prep will look a little familiar as it was used in an earlier example. So the powder samples we'll typically take and press into a pellet whenever we can. It's going to make for a good analysis surface, and it's a stable material and reusable, like I said. So this is fast and can take a few minutes. In the case that the sample does not press on its own, we will mix binder up to 10-20% in this case. We prefer disposable materials for mixing. We like to prevent any cross-contamination where possible. And here's an example of like a benchtop mixer that would be used in this case. This is the one from our prep lab, actually. So we'll mix our sample in our binder really well. So once it's mixed, we're going to be ready to press. So we'll take a weighed out portion. Again, this is going to look familiar. We're going to put our sample in the middle of one of these rings. It could be PVC or aluminum, and load our die on top. That's then going to be pressed in an automatic press again. In this example, we pressed it 10 tons. And then these samples were then run on a 4 kilowatt system. So you can see, like I said, that sample came back again. So this is going to be a very stable material that can be reused. So from those results, the first thing we'll talk about is the semi-quantitative results. So we'll collect spectra. We'll talk about the spectra in a minute, but the results on their own, we had a good comparison of two samples between WD-XRF and ICP for these NCM powders. So again, this is semi-quantitative, meaning we did not do any additional calibration. This was factory installed calibration, instrument out of the box, no additional work. And you can see that the ICP and WD-XRF results coincide really nicely. I mean, 0.85 nickel versus 0.846 nickel. The ratios are almost exactly the same. So it's a good option in the case of these types of materials. You don't have standards. Factory calibration may do just fine. So this, again, is an example of aiding in that mixing ratio to make sure that our NCM ratios are to be expected. The other thing that comes out of a semi-quantitative analysis is that spectra. So this allows us then to view all the other peaks of analytes present. And this is a zoomed in view. But you can see for both of these samples, we do have trace levels of iron that were detected that otherwise we wouldn't have known about. Iron could be an issue for these materials and cause degradation. So being able to identify all elements within the capability of a spectrometer without even having to calibrate is a huge help and time saver in this case. The added bonus of quality check for product without additional work is nice to have. So in the case of iron, like I said, something we probably weren't hoping to see, but it's good to know it's there in the case of this could cause degradation later. And again, we wouldn't have known this had we just ran a quantitative calibration for our typical NCM. The next example I have is a graphite anode example. So in this example, a sample is poured into a cup with a film across the surface. So we can see the surface here. And here's the powder sample that was placed in. So making the couple take a couple minutes. You're just going to weigh out and pour in your sample. This is going to be 100% recoverable at the end, so you can continue with other analyses as needed. Or in the case of anything where precious material, 100% recoverable. So we're able to build this type of cup and apply pressure. So this could go in a tube above or tube below instrument configuration. So we can flip powders upside down for those that like the tube above, like myself. It's not an issue. So we'll just press and apply pressure. It's going to give us a nice analysis surface. And now we can defy gravity and use the tube above system. So here's the actual sample that was produced. So this can help us with quality control for our incoming materials in this case. So this is a semi-quantitative analysis again. So the first thing we're going to have is spectra. And there are a few elements that showed up in concern that we weren't anticipating. There's high sulfur content in sample B. And then varying amounts of iron in samples A, B, and C. So these were commercially readily available materials. And this much sulfur, this much iron could be a shocking find for some, as it was for Bob in this case. He was pretty shocked by this. So along with the spectra, again, it's semi-quantitative. We get quantitative results. How much iron is there? In this case, it was 180 ppm for sample C, which was our high iron peak. And then almost 3,000 ppm of sulfur in sample B. So again, this was a really easy, quick screening technique for incoming or quality control of products that are in your lab or in your facility. Again, no calibration was needed. This was done in just a few minutes. And then our final example is going to be our black mass recycled material example. So this was actually done on an energy dispersive X-ray fluorescent unit. So begin with our black mass. This was prepared in a cup very similar to what was ran earlier and was loaded into our next QC plus unit. So this is actually our smallest benchtop unit we have. This is the one that I was joking you could take home in your backpack. So running on the next QC plus for semi-quant gives us a wide characterization of all the metals in this case for that material. So again, in the case of recycling, I know you've got everything but the kitchen sink in there. In this case, you'd probably balance on carbon and get an idea of what's in there and where to head next with this material. So I just want, as long as you can understand that there's a lot we can see with very little work in this case, just seeing an idea of what this material has in it. And now that we've heard a little bit more about XRF and our examples, I think we've got one more question.
Okay. So this is going to be the last question we have for the audience today. Okay. So after seeing all those application examples and Amber presented, do you think XRF can be useful for your analysis needs? This is a moment of truth for you, Amber.
Can I have a B? I want a B at least.
Okay, about a half of you answered it. So far, looking good for you.
All right.
Okay, I'm gonna wait a few more seconds. Okay, so I'm gonna close it in 3, 2, 1. Okay, let me share the results. Everybody said a yes.
Yay!
Mission accomplished.
That's great.
Well, good. I'm glad to hear that everyone's in agreement so far.
So Amber, we also have a couple questions from the audience.
Yes, sir.
One is it possible to share the presentation slides after? And yes, we will be sharing the entire webinar recording after this event. And then the next question is more technical. It's the semi-quant analysis comparison for NCM looked great. When do I need to do calibration for true quantitative analysis?
So my usual way of doing it is to try it with semi-quant, and to see, you're going to test with a standard and make sure, are you getting what you expect or not? In the case of semi-quantitative analysis, you could have some variation. In the case that you're caring about 1 or 2 or 3 or, a few ppm difference in your material is a huge deal. In that case, I would definitely calibrate for it. I'm very cautious and like to say you could have up to 10% variation in semi-quant. Typically, it's not the case. We typically see a lot less than that. But if that scares you, that would be a good indication that maybe it's good to go ahead and calibrate. But I'm always one to let's try it and see first to make sure. But NCM powder seems to do very well with the semi-quant.
Very good. Thank you.
No problem. All right. At this point, I think we're just going to wrap up. So at this point, we said we've answered the question of what is XRF, and hopefully we've convinced you that we can look at a wide range of materials and elements. There's a variety of instruments on the market. They come in different shapes and sizes. They come in different analysis flavors. So hopefully there's something that can meet your need and your budget. The next, why use XRF? So obviously we hopefully understand at this point it is non-destructive. We can usually recover your sample at 100%. It's very easy to prepare materials, and we can find a prep technique that can meet your needs and what your lab is able to handle. And the speed of analysis, it's a very quick analysis, and it's very quick for setup and calibration in the case that you do go for calibration. The third being, where is XRF used? We talked about a few different applications today, more on the refining and recycling process. We do see it commonly used in mining, and hopefully we'll see it more and more widespread as time goes on as well. And last but not least, how is XRF used? So we covered 3 examples today, the black mass recycling screening we did at the end, the graphite anode, and the NCM cathode powder. But there's many other applications. There's only so much time in the day. So at this time, I think if there's any other questions, hopefully we can answer some questions for you.
I do not see any other questions at the moment, Amber.
All right.
Okay, so let's wrap this one up. So as I mentioned earlier, a recording of the webinar and also the slide deck will be available tomorrow, and an email will go out to all registrants with a link to the recording page. And links to the resources mentioned today will also be shared on the same page. And all the application examples you saw in Amber's presentation today, and many more, and other application examples, are available in our battery ebook. And I'm going to put a link in the chat so that you can go take a look at it. So you can download it from the link I just put in the chat. And this ebook has the process infographic plus all the application examples that are related to different stages of the process. Now, this concludes this episode and this battery webinar series. And let me grab another link. Okay. So there you go. So this is the last episode of the webinar series for the battery analysis. And if you missed the previous episodes about X-ray diffraction, pair distribution function, and computed tomography analysis, And you can watch them on our website. All the recordings are available there. Okay, with that, thank you for joining us, and we hope to see you at the future webinar series.
Thank you.
Thank you.
Thank you.